Welcome everyone to the compilation session, and here we will have five talks. And the first talk, Don't Look UB, exposing Sanitizer-Eliding compiler optimization. Raphael will give a talk. Okay, thanks.
Yeah. Well, thanks for the introduction. So as said, the title of the paper is Don't Look Up, exposing Sanitizer-Eliding compiler optimizations. So as you might have guessed from the title, this talk is about sanitizers. So what are sanitizers? Well, it's probably one of the most successful bug detection tools we currently have. Various people are using sanitizers to find bugs fully automatically at a large scale. So what do sanitizers actually do? Well, the idea is pretty simple. You compile your program, and sanitization is essentially just one more extra step in your compilation pipeline where we add checks for certain kinds of bugs that end up in the final program. You run your final program with some kind of input, and if the checks by inspecting your program state, detect some kind of bug, they make a nice error message, and they abort execution. Now, sanitizers are a compiler feature. Compilers don't have like domain knowledge, don't know if you're doing like a banking application or whatever. So all the checks we can do automatically have to be essentially focused on the few things the compiler knows, which is essentially just your programming language. So what we end up with is most of the checks that are generated by sanitizers are for undefined behavior. So now what is undefined behavior? Well, it's essentially a part of certain programming language standards, where essentially the standard says there's some things, and if you do these things, then you're off limits, so your program has no more any semantics, and essentially whatever your program does, it's valid and conformant to the standard. The classic example is, buffer overflows in C. Your program might crash, it might behave correctly, it might delete all your files. That's all compliant with the standard. Now, there's a reason why we have UB and language standards. It's not just job security for like security engineers. The main reason is performance. By not doing these checks and various other things, we can go faster. So if sanitizers re-add these checks, of course we go slower again, and that's a big problem. We want sanitized programs that are also fast because we use them, for example, with random testing, where we run many inputs in succession, and that's how we find bugs in programs. So how do we make sanitized programs fast? Well, in practice, what we do is we just use the optimizer. It's like right next to the sanitizer in the same compiler we're already using. So, let's just turn it on. That's what everyone is doing. So how does the optimizer make programs fast? Well, it cuts away everything that's not part of the observable behavior. So that's also defined by the language standard. Now the question is, what about this undefined behavior thing? Can it also cut that away? And the answer is not only yes, it can cut it away. Undefined behavior is not part of the observable behavior of a program. The optimizer actually assumes that your program is completely well defined. Now if you think about it, I just made two completely opposite, or we have two components with completely opposite assumptions about the program. Sanitizers try to find UB, optimizers assume there is no UB, and we mix those in practice. So we're kind of curious, like, this seems like an interesting situation. So the questions we had is, first, if we have a compiler that has a sanitizer and optimizer, how can we figure out whether these two work together as intended? With the main focus being that we want reliable bug detection with both enabled. The second question is, once we have some kind of testing approach, let's apply it to some real sanitizers or some real compilers and see what happens in the real world. And the third question is, well, if these compilers we have, if they don't work correctly and we have blind spots, so bugs we just can't find because of this mix, are we also missing real bugs in the programs we're like trying to find bugs in? So let's start with question one. How do we do it? How do we find out whether sanitizers and optimizers work together? So our idea is we do differential testing. We have some program P, let's assume some opaque contents, and we compile it twice. We compile it without optimizations, but sanitizing enabled. And then we compile it again with optimizations and sanitizing enabled. And we get two different versions of the same program out. And our idea is, well, if the unoptimized program has a bug in it, so we give it a certain kind of input, the program runs, and some sanitizer reports an issue, then we want to also find the same or maybe a different bug when we run the optimized version. If this doesn't hold, then we can assume that the program that shows this kind of behavior demonstrates an optimization that removes a sanitizer check that we actually needed to have in the final program. So if we just have one program B and we do this once, we don't really get a really good test coverage, and we probably won't find anything. So we want to have as many programs P that we give to the compiler as possible. And to do this, we first have to figure out what are our constraints for P. Well, in general, we only have two constraints. Either we have a program that leads to a sanitizer report, in which case we just do our normal testing process, or it's well defined, in which case we lose a test cycle, but it's not a big problem. There's a third constraint, which is a bit more vague. And this is, first of all, we need to be deterministic. That's the minor part. That's kind of easy to do. But the bigger problem is we can't have any kind of UB in there that's not sanitized. So you have UB, and there's no sanitizer checking for it, because then we just go back to like having a program that has no semantics. There are no deterministic checks anymore. But assuming we filter out these kind of programs that have unsanitized UB, we can pretty much just throw everything into our test oracle, and we get test cases out that demonstrate optimizations, that remove checks that shouldn't have been removed. So we thought, great, so we have this testing scheme, let's use it on a real compiler. So we started testing Clang, which is probably the most complete sanitized implementations we use, and it's also the most widely one we are currently using to find bugs. And the first thing we noticed is, well, a lot of the checks we have in Clang, they just disappear when we turn on optimizations. And we were kind of curious what is happening. Are we just holding Clang wrong? Like, what's the issue? So we did some root cause analysis. And the first thing we found is that, well, the issues are not evenly distributed. There are 3 sanitizers in Clang. One of them, UBSAM, which is some collection of various checks that don't require any runtime, they're doing quite well. Like, those are essentially not affected. But on the other end, we have ASAN and MSAN, which do like generic memory errors, and those are heavily affected. So we were curious, like, what's happening? Is it an implementation issue in the passes or what? And you might be able to guess what the issue is if you look at the position of these passes in the simplified diagram in the compilation pipeline of Clang. Well, what you can see is that UBSAN, which is fine, is before the optimizers, and the passes that are not fine are run after the optimizer is run. So clearly the optimizer is doing something it shouldn't do. Well, what we found out the optimizer is doing is it's becoming very, very good at detecting and exploiting undefined behavior in programs. One of the things, or some of the things it knows about are things like uninitialized values. It knows whether local variables are uninitialized. The same for struct fields being uninitialized, or even array members being uninitialized. It knows the semantics of many C standard library functions. It knows, for example, that string length looks for a null terminator and that it's undefined if there's no null terminator. It knows how memcopy works and that it has undefined behavior. It even knows about heap memory management. It knows how malloc and free works, new and delete. It knows that double frees are undefined and use of the frees are undefined, and many, many more things. And it can just detect these things by looking at a single function, which most of these passes are implemented. But if inlining happens before, it can even do this kind of detection across functions and even files with link time optimizations enabled. So what it actually does with all this knowledge is it has code that has bugs in it, bugs that actually would be detected by MSAN or ASAN, but it replaces those. And it gives us code that's actually free of bugs. And those get sent to ASAN and MSAN, and there are no more issues that could be detected. Now, you might say, well, this sounds actually pretty great. You know, the optimizer is making our programs faster. It's also fixing our bugs. You know, another win for Team Optimizer. But it's not that simple, actually. So to be fair, in a lot of cases, actually, the optimizer is actually fixing bugs. There are programs that are broken, and the optimizer actually fixes the bug in the way the programmer intended, essentially. And more often than not, we just look what the optimizer did. We made a patch out of it, and we send it to the people that just applied the patch that was kind of already done by the optimizer for free. But in other situations, it did not fix the bug. It actually essentially just exploited it for the attacker, essentially. So in the case, for example, of uninitialized variables, and it detects that the variable is used uninitialized, it just guesses a value and it adds it into the final program. This is fine, like there's no UB if you just use an uninitialized value, if you use like a constant 0 in the if, so MSAN says this is fine. But the original program had an uninitialized use, and one of the 2 branches is now just taken by a coin flip from the optimizer. For other bugs, the optimizer fixes it, of course, but this is not guaranteed. Like the optimizer does not make any promise to actually fix those bugs, even though it currently does it. But if you move to a different compiler version, or you just change your flags, things just start breaking again. So with all that knowledge in mind, so we know that these things have blind spots and that the current sanitization search essentially misses bugs. Well, are we missing bugs in real world programs, or are we just finding corner cases that don't really matter? Well, so we try to think like, how can we find these bugs? And we were pretty confident we could find bugs because many of the patterns that are actually exploited are so widely applicable to various kinds of software, it's kind of obvious they actually exist. But we still try to find actual bugs just to show that they actually exist. So we came up with 2 different approaches. The first one is, well, let's just do random testing without any optimizations. Now you might think this is very slow, And you're actually right, it's extremely slow. Like we had probably for a while the slowest fuzzing setup on the whole planet. And we decided to use it on Google's OSS fuzz projects. So that's a bunch of open source projects that get essentially constantly fuzzed by Google with like huge hardware clusters. And we had like some tiny machine that runs the slowest setup possible, and we just tried to find bugs in the same projects. The second thing we came up with is, well, we know the optimizer is removing those bugs, and sometimes you can actually spot by observing the optimizer that it actually found a bug and tries to fix it. So what we did is we wrote a static analyzer that does nothing else than just watching the optimizer do its thing, and we wrote a pattern matcher to see, oh, this is code that we know is not only problematic, but it also gets missed later on then by the sanitizer, and we just essentially made a small error reporting out of that, and we generated reports by compiling like a large set of open source projects. All in all, we found about 19 bugs in various open source projects, and that's the number from the paper, and it's just the tip of the iceberg. By now, we found more issues. There's a bunch of issues that we didn't add to the paper because someone else found them already and whatnot. So over time, this number will just grow until we fix it. Bugs are some kind of regenerative resource in some kind. So to summarize, do sanitizers and optimizers work well together? Well, unfortunately, at the moment, they don't. How can we test this? Well, differential testing turned out to be, in the current state, actually pretty sufficient. Are we missing bugs? Again, unfortunately, yes. And the last question, how can we fix it? Because you might think, well, that sounds pretty easy to fix, especially if you look at the whole compilation pipeline picture I just showed. And if you think there's a simple fix, then I have to disappoint, and that's one of the reasons why it hasn't been fixed yet. But if you want to find out what the reason is, you have to read the paper, which you can do by scanning the QR code. And with that, thank you very much, and let's go on to questions.
Yeah, thanks. Yeah, thanks, Raphael. And is there any questions? You can come up and stand. Yeah.
Hi, Andre Lasko from King's College London. Do you think this optimizer is inherently flawed if it essentially changes the binary compared to the code you've written?
So one of the things I've also tried to make clear in the paper very clearly is I don't think it's either the optimizers or the sanitizer's fault. The optimizer actually does exactly what it should, and actually if you go to the optimizer people, they would tell you, no, this is what it's supposed to do. And it actually, like, if the program was correct, it should do the right thing. So I don't want to say that either the sanitizers or the optimizer is correct. It's more of like a communication issue, I would say. So I think the short answer is I don't know who to blame, and I don't want to blame everyone. It's like complicated systems and issues happen. So short answer is I don't know who to blame.
Thank you.
Hi, I'm John Regier from the University of Utah. So I'm gonna ask a question, but I just wanted to say something first. I do know who to blame, which is it's the unsafe languages are to blame. That's the entire problem here. So I was hoping you'd tell us what would happen if we happen to run for example, ASAN instrumentation before running the optimizer.
Well, this is the thing why I wanted to get people to read the papers. I don't know. Well, I guess I got asked now, so I have to do it. So the reason, so what happens is actually it works actually pretty well. There are some minor details, but generally speaking, it works well. Now, there's a problem, which is if we do it before the optimizer runs, things get much slower. And the reason why things get much slower is because ASAN adds a bunch of weird code in there. Like, I'm not sure if you have seen how ASAN code works. It takes pointers, it starts XORing stuff, the addresses and whatnot. And if we do this, the optimizer is like, well, you do like strange stuff here, and it just leaves the code as is. And we actually have sanitized binaries that are much slower. So in fact, I have backup slides for this. If we move the pass early, we see the overhead of ASAN and MSAN, that's the left and the right bar, like blue and orange, become much larger if we move it as an early pass. So for ASAN, it's okay-ish. We get 40% slowdown, which is probably like several decades of research into that area undone. But for MSAN, it's actually really bad. Like it goes up to like 340% overhead from just 160. So the short answer is we can do it, but things get really slow. It's still better than running on without optimizations, but well, we could do better. But you have to read a paper for that. Sorry.
Thanks.
Hi, Konrad Hundhana from Fraunhofer. Thank you for your talk. My question is, right now, if you develop a sanitizer and you want to evaluate it, you probably use a test suite, for example, a Julia test suite, which is 0 optimized. and then you have no chance of actually detecting these issues. So I wonder if you have some better test suits for sanitizers, which you advise.
So at the moment, no, we actually want to work on that, and there's like a project going on for that. But I want to say to Juliet, you actually can find quite a few places where those things actually happen by turning on like 01, 02, or 3 for Juliet. And you will see that quite a few programs just disappear to nothing. I should mention that like it's not blaming Juliet or anything like that. Well, actually, it's like a good thing for Juliet, but Juliet is more like a static analyzer suite we're just using to test dynamic analyzers. So I don't know. It's a hard. I don't know anyone that's actually better, so I couldn't tell you. I think right now we're stuck with Juliet and Sard is I think the other one.
Thank you.
Hi, Devin from Apple. Great talk. One thing I'm curious about is whether you saw the optimizer removing checks from UBSAN in particular. And the reason I ask is because UBSAN is commonly used as a hardening mechanism in production rather than for fuzzing or testing. And so that would be even more problematic. Is that something that you see?
No, so in general, well, so I think there's one thing we excluded pretty clearly, which is generic optimizer bugs. And I think the only place where we ever really, like we have one case where it removes a UBSAN check that it's very contrived, and I don't think it really hides anything in real life. You can find UBSAN checks removed, but I think the few we found were just generic optimizer bugs that we just run into. I should point out that, and I had this on the previous slide, but you know, there's always short on time. If you have a program that has actually an ASAN or MSAN failure, well, especially ASAN, and you say, okay, I tested with ASAN, and then you ship with UBSAN in production, it actually turns out that's a pretty bad idea, because one of the things UBSAN does, it essentially deactivates a lot of optimizations. Like a lot of pointers start escaping, so a lot of optimizations are like, well, we don't know what happens. And the problem is that a lot of the ASAN bugs, like double freeze and whatnot, actually get reactivated. So you can have a double free bug, it gets optimized out, and ASAN doesn't see it. But if you use it with UBSAN in production, UBSAN adds checks that break the optimization that fixes the double free, and you actually have an exploitable double free. So it's not a double free that gets reported. It's actually a double free that actually is exploitable in like, there's no warning. You just literally have a double free where you can write arbitrary into the memory. So yeah, I think the situation with UBSAN is, it's a good sanitizer, but it's actually kind of problematic that only like half the setup is broken at the moment. So I hope this answers the question.
Thanks.
Okay, no more questions? Okay, thanks to the speaker.
Right? Thank you all.